video for the third year group project, and in specific how we've been working remote. So, overview. First of all, I'm going to walk through what we did in our third year group project as part of the undergraduate Maths and Engineering course at Imperial College. And then I'm going to go through some of the specifics of how we're still here, still working, still trying hard despite lockdown, and how we're using Microsoft Teams, Slack, video calling, and all that modern technology to still press on. So the undergraduate group design project is 25% of third year, effectively. It's a very large portion of coursework. So there are 5 large groups and group projects running every single year after exams for about 5 or 6 weeks. The idea is to simulate industry and the atmosphere of a design bureau. Of course, this had to be moved remote this year. And essentially you track an idea right through from the stages of ideation, through conceptual design, straight through to preliminary design of fairly detailed components and sub-assemblies. Our group design project was on a wholly reusable launch system, which was a great success, as I'll demonstrate and show. So what is a wholly reusable launch system? So rockets are expensive things and are forecasted to be a booming market. But the problem is that they're ridiculously expensive. Through some analysis, we boiled down that this is because a rocket is not reused like an aircraft is. You know, you can afford to fly on an A350, which costs vast sums more than a conventional rocket, but yet very few people can afford to put a payload in a rocket because that rocket is single use. So we were targeting small satellite markets for about 140 to 160 kilograms worth of payload to put it into low Earth orbit. So as you can see on the right, this is the kind of thing we're going for. So a reusable launch system consisting of a launcher and a recovery vehicle. So we were designing the recovery vehicle in a group of 25, with 25 students also designing the launch vehicle. So we took 3 different concepts, pre-conceptual designs of what kind of aircraft we could have to recover a falling rocket payload. So we had an aircraft design in the bottom left. We evaluated a helicopter, which is in the middle. In particular, this is a synchrocopter, so it's a dual-bladed, dual-rotored kind of helicopter design, and we also went for more exotic kind of tilt rotor, tilt fan ideas. Basically, we needed something which could go to a decent altitude to collect a very large payload and be highly manoeuvrable. So the rocket would essentially fly up, fall back down from space when we catch it. So the concept we went for was the helicopter, and we ended up designing this, which is a synchro-capture, as we named it, which is a syncropter, so it's a dual-bladed unmanned aerial vehicle, which is also a helicopter in style, which can go up to an altitude of about 20,000 feet and recover a rocket payload as it's falling. So on the bottom right, we've got a basic mission profile for what we're trying to do. So the rocket takes off, it splits off, the first stage booster falls down, it's got a drogue chute which expands to a parafoil, it then glides down and we capture it with this helicopter, we drop it off on a ship, so it's a naval-based helicopter as well, and then we essentially do the same for the upper stage when it also returns, which is something totally novel and is not currently done. So essentially we need a really beefy helicopter to get up to that kind of altitude, 20,000 feet, where we wanted to try and have our maximal ceiling to carry a very large payload, which was half of the maximum takeoff weight with the payload. So that was what we intended to do. This is the design we came up with as a cutaway view with some of the sub-assemblies and systems listed. It was a mainly space frame design because basically we wanted to take all the forces which would go into the frame in the kind of lightest possible configuration with just a very sleek aero shell over the outside of it, so you can see some of the internal workings there. So the helicopter itself was designed using every tool we had available for us in a remote setting. This involved a lot of generative structural design, which I'll go into, a decent amount of finite element analysis, which you learn early in third year at Imperial. And also we did things like engine performance simulation, which built on the second year turbo machinery course, and also the third year advanced propulsion for those students that took it this year. So we've got systems layout in the lower left-hand design, which also shows you the slanting of the engine and the transmission. I'm going to try not to go on about the transmission too much, but that was my little baby. That was what I worked on. So in terms of the transmission, it says that, and it's the next slide. This is the transmission. So essentially, I designed it for a very high efficiency to calculate and carry that power through from a 1,600 horsepower engine to which was operating at 12,000 RPM, straight through to the actual rotors themselves, which have to travel a lot slower as not to breach any kind of sonic requirements and shake themselves apart. Being remote working, one of the things for me was the fact that I didn't really have access to any CAD software at home. I didn't feel like remote booting one of the college machines to do it, so I ended up relying a lot on hand drawings and PowerPoint, hence a slightly crude drawing on the right. But we built in some fairly detailed stuff to it, including a health usage and management system to detect kind of oil shards in the transmission themselves. So getting back onto the generative structural point, two of my colleagues worked a lot on the structures and airframe side of things. So this was their kind of process in terms of mapping out where the geometry could go, then using that to guide the design of the space frame with various bounding box requirements around certain key components. So I had some good friends and colleagues working on that. In terms of a bit more on our electronic design process, because of the relative advancedness of how software's come on and the fact that everything was done remote, we were almost pushed more into seeing, well, what could we do which totally wasn't in person? So we ended up relying on a lot more machine learning optimization in various things, such as even the mission profile itself and computational fluid dynamics, which is a third-year option course for those of you who want to take it, and it's also covered later in fourth year in advanced computational aerodynamics. So this modelled things like the rotors, which are a weird spade-like device called a burp, blade tip, blade end, which is shown in the lower right-hand side. I had a friend work on the structural layout of the rotor as well, so he was working close in tandem with the guys in the aerodynamics section. And the aerodynamics section also governed the kind of aero shell we had, which is shown on the lower left. This is using a software called Star CCM and also ANSYS Fluent. The recovery mechanism was done by a member of my direct subgroup, so I was in the subsystems and propulsion group. So this covered things like the transmission, the oil system, the engine, but also the actual capture mechanism for this capture instant when the helicopter swoops down and catches this parafoil laden rocket part as it's descending from its post planetary journey. So in terms of the design mechanism itself, it was building on existing technology which was pioneered by the CIA in the 60s for recovering spy satellite photography and actual film, but also used unique features such as morphing airfoils, which is something which hopefully we'll see a lot more of in the future. So not conventional slaps and flaps and slats as you'd find, but actual splitting rudders and using little piezoelectric devices to try and control the drag exactly to try and match as much you can these velocity vectors when you try and capture these things. In terms of the modelling and simulations, we had a lot of colleagues working on the flight mechanics modelling of a helicopter, which is difficult, and especially when it's got two rotor blades, it's more than twice as difficult because you've got all these kind of wake interactions coming off the rotor blades. They also used X-Plane to build a model, and it did actually fly, which I was pretty happy with, and it was darn manoeuvrable and nimble when it did. So we had a few of the guys and gals on X-Plane flying around mock airfields, trying to do test runs of it. So that's what you can see in the lower left here. These are little bandwidth of how precise they could be with their manoeuvres. So how do we achieve this whilst working away from campus for 6 weeks post-exams, which were also done remote? Essentially, we relied on Microsoft Teams and remote working for almost everything. So this is how we coordinated 25 of our students on the recovery side, 50 in total, including the people who are actually building and designing the rocket themselves, and students who were spread all across the globe. So I had a lot of colleagues in Singapore, the Americas, the Middle East. So we're working with a big time difference, which brought up its own issues. So essentially, we ran everything remotely across Microsoft Teams for the recovery team. So that was the helicopter design group, and then the launch team had Slack, which is another service which can be used for remote working. All of these projects were student-led, so we had 3 highly capable students who were selected pretty much at random, who led us and led a group of 25 other students, which is a great thing. And we had one centralised communication channel through Teams, and it was great. You could get anyone whenever you wanted. We had a great degree of freedom, and especially decisions were allowed to be made at a ridiculously low level as long as you kept everyone else informed. With the launch team as well, for anything like the payload size itself, we used a third-party website called Valor Space, who were able to sponsor the actual launch team on what they needed to do. Meetings were organised when needed. We were able to host meetings online and get pretty much everything we wanted to do done exceptionally efficiently. There was a bit of conflict resolution at some points, but it was a great experience. A good friend of mine said that he'll miss the random times of the day calls, which I think we all will, and you'll see what I mean on the last slide. But essentially, Teams facilitated all of our meetings. It was a great ally to us. It enabled us to present weekly meetings, weekly briefings and updates. We had a WhatsApp too for informal conversations, which was nice in its own way. It was a way of de-stressing and kind of doing a little bit of relaxing. But it's difficult to convey ideas. So as well as this graphic modelling, which we've got on the left, an example of, a good old hand-built techniques also came into use, which is where I can see a little scratch-built Lego Mega Bloks model there to try and show other students what the concept we're on about. I remember at one point, to try and get the recovery capture mechanism, I actually got a wine opener, and we were trying to work out how to get little tines and geared parts to move away from each other, and that was the first example I could think of. So it's amazing what you do come up with in your ideation stages. So remote working, it's got loads of positives. 24-hour workday can double your productivity easily. Flexible working hours, you can work whenever you want. The only problem is that's its own negative, because you have to work at some point, but it's very nice to put it off. Just like your location of work, it'd be brilliant to be working in the office environment on campus, in a lecture theatre, in a PhD study room with your peers and colleagues, but you can't, so you need to try and work where you can from home, which brings up its own communications and contact issues for different people. Especially when you've got this time zone delay. That said, being able to work online, there's a clear trail of who's done what, especially if you document it very well and you take minutes of all of your meetings and things like that. But as I've mentioned, concepts can prove very difficult to explain to other students when you're just talking over a screen, which is why it's good to have an engineering practice in terms of what's the standardised way of designing things, and probably only having one or two people on your CAD can sometimes be helpful, as was the case in this project. What did I get out of it personally? Well, as well as a nice looking report with an obtusely long title, it was an exercise in overcoming obstacles and conveying ideas, trying to work out how best to converse and accept peers' ideas in various things. It showed to me the utter efficiency of online working. As much as can be said to its detriment, I personally found working online to be a lot more stimulating, and also, you get this appreciation for what it's like to interact in person, have your downtime in person, but also move to a more online setting. It was a great proving ground in how to work online. It gave me a love, in italics, for helicopter gearboxes, something I don't think will leave me, but also the fact that with this shift online in fairly unprecedented times, there is a certain developmental bond which you get with your lecturers and academics and supervisors and these things, and it's been a good experience for that, and to see how things work away from just the lectures of first and second year onto more in-depth and novel project work. And it's a shame to think that in my degree, to be honest, after this, there won't be as much opportunity for group work as there has been. Third year is probably the most group work heavy of all of the years, and we move on to more of an individual project and a deeper understanding and relationship with academics as you move on to your fourth year final project. It was a great team building experience. I loved it. We ironically named a fair few of the meetings, as you can see in the lower left, where we just had to do more CAD and various things. We scheduled downtime as well, so every weekend we'd have a Jackbox or alternate party game, as you can see on the lower right, which was done through Google Hangouts. It was a great build of positivity in the workplace as well. I've drawn a lot close to people in my ear who you wouldn't usually get to work with if it wasn't for these group work settings. So this is the mega meeting which I mentioned earlier. This meeting was 10 hours 35 minutes. It started about 6 o'clock one evening, which was the final evening of the project, as all things do, and it went on until about 3 o'clock in the morning, 4 o'clock in the morning. 6 of us just bashing out the final poster, and this is probably my best memory from the entire project, and it's something I'll really take away from me, really take away with me. Of course, with all things, they end up being a little last minute and rushed, but it was nice to see everything come together and get some really good deliverables and results from this project. Highly recommend it. It was great fun, honestly. Just I've got a massive smile on my face now just thinking about it. Thank you very much for listening. Hope this has been informative, especially to people who are considering Imperial or evaluating how you can still work online or remote in these times. It's definitely possible. I wasn't paid by teams to say anything on their behalf, but I think it's a great software. And credit goes to the people who made the GDP the experience it was, the academics who facilitated it, and good friends and good colleagues and good learning experiences.